Okay, so intermolecular forces are interactions between molecules or between ions, or ions and molecules. And we're going to go through a few of them. So let's start by talking about dipole-dipole forces. The dipole-dipole forces only exist between polar molecules. So you first have to identify it as a polar molecule, and then if it is, you may write dipole-dipole forces next to it, okay? Dipole-dipole forces are like medium in strength, generally speaking. So if you've got an HCl bond or HCl molecule next to another HCl molecule, you know that chlorine has the partial negative on it because it is drawing the electrons to itself because it is more electronegative than hydrogen. And so when you've got neighboring HCl's next to each other, since the hydrogen is electron deficient and it has the partial positive on it, the opposites will attract each other, and these dashed lines that you see in between the HCl's, that is your dipole-dipole force, okay? The more polar the molecule, meaning like the stronger the dipole moment, the stronger the dipole-dipole forces will be, okay? And let's take a look at a special type of dipole-dipole force, which is known as hydrogen bonding, okay? So hydrogen bonding is only going to exist in a molecule that contains one of these three bonds, okay? So if the molecule is polar and it has one of these three bonds, it has the ability to hydrogen bond with something else, okay? And the way that this happens is, let's say you've got a water molecule, which looks something like this. Water is a polar molecule, and it contains an OH bond. So therefore, it has the ability to hydrogen bond with something else. So what happens is, if I have a neighboring water molecule, the hydrogen will be attracted to the lone pair of electrons on the highly electronegative atom O, N, or F. And this right here would be my hydrogen bond between the water molecules. Be careful when you're doing this. The OH, NH, and FH bonds that are inside of the molecule, those are not hydrogen bonds. The hydrogen bonds exist in between the molecules themselves. So since O, N, and F are highly electronegative, here in this OH bond, the O is going to draw the electrons away from hydrogen, which makes it electron deficient and has that partial positive on it. It is so desperately attracted to the lone pair of electrons on O, N, or F that it practically creates a bond with it, and that is my hydrogen bond. Hydrogen bonds are going to be the strongest of the intermolecular forces. Intermolecular is often abbreviated IM. Just keep in mind that it has to be a polar molecule first and have one of those three bonds present in order for it to hydrogen bond with something else. So the explanation in words for what I just talked about is here, where the partially positive hydrogen in one molecule will be attracted to the lone pair of a partially positive negative atom of another molecule. This partially positive negative atom of another molecule is going to be your N, O, or your F in another molecule, okay? Let's turn the page and let's talk about what hydrogen bonding causes. Since hydrogen bonds are the strongest intermolecular force, they tend to cause really high boiling points. So they're going to cause things to change. If you take a look at the next page at the graph, here they're showing you how the boiling point for water and HF and NH3 are higher than expected. These green, blue, purple, and red lines are the general trends for boiling points as you go down a particular group, and you can tell that these are extremely high. And this is due to the fact that all three of these hydrogen bond. It's going to take a tremendous amount of heat energy to break the intermolecular forces between the molecules and get them into the gas phase. Okay, something else that you should know about hydrogen bonding is, and you probably remember this, is it is involved in DNA base pairing in the double helix. So at the top of the next page, they show you the double helix, and they show you between thymine and adenine how you've got hydrogen bonds stabilizing them. Okay, let's move on to London dispersion forces. So a third type of intermolecular force is called London dispersion forces. You may see these abbreviated as LDF, or you may see them abbreviated as dispersion forces, and everything has these. These are generally the weakest of the intermolecular forces. And so that means in the box on the lab for every single substance, you would write LDF because everything has them. Okay. London dispersion forces, if you have something nonpolar, then it would be the only intermolecular force that it has. Okay. There are some things that will cause the strength of London dispersion forces to increase. So those could be things like the electron density of a molecule, how easily you can distort it or polarize it. It also could be affected by the molar mass of something. So here, let's highlight let's see, electron density. Okay. So if you've got a really bulky molecule, like if I've got something really small versus something really large with a bunch of branching and chains in it, then this would obviously have the higher electron density, and the electrons are more easily moved, and so therefore this one would have the stronger London dispersion forces than this teeny tiny substance would. Okay. Something else that you probably want to understand in terms of London dispersion forces is what happens is, since electrons are constantly moving, they may move to one location or another, and that will cause a neighboring molecule's electrons to move as well. So let's say for some reason you've got the electrons, these are, I think, hydrogen atoms. Doesn't matter what they are. But if I've got an electron in here, and all of a sudden, for some reason, the electrons move over to like one side of the molecule temporarily, you would get a partial negative on one end just for that instant, which would cause a partial positive on the other end for that instant. And then the electrons in the neighboring molecule would then move, because the electrons would then be attracted to this partial positive that's on this side of the molecule. So the electrons will move suddenly, and that will cause a partial negative on this side and a partial positive on this side. And then you will end up having the attractive forces in between the molecules. So these little tiny attractive forces, which are these yellow dots, this would be a London dispersion force, which is just temporary. It's just instantaneous. Okay. And then it goes away because the electrons move again. Okay. So this is simply caused by electrons constantly moving. You're getting these constant partial positive and negative charges all over the molecule. And then that causes the neighboring electrons to move, and you get these temporary, short-lived, weak interactions between molecules known as London dispersion forces. Okay, so polarizability is basically when you can easily sort of influence the electron movement or the charges in these larger molecules. Okay. Over here, they're showing you the difference in melting point and boiling points of diatomic elements on the periodic table. And the reason why they're showing you this is because fluorine would have the lowest atomic mass, and then astatine would have the highest. And this will influence the strength of your London dispersion forces. So this one will have, the fluorine will have the weakest London dispersion forces, which means it takes very little energy to sort of pull those particles apart. That's why you have such a low melting point and boiling point. Whereas the astatine would have the strongest London dispersion forces, has the highest molar mass, and therefore would have a really high melting point and boiling point, because you're going to have to provide more energy to break apart those intermolecular forces between the particles. Okay? Okay, now let's talk about ion dipole forces. You will not be writing ion dipole on anything on the lab. And the reason is because ion dipole forces only exist in solution between a freely moving ion and a polar molecule. So generally speaking, ion dipole forces will exist between a salt that is dissolved in something like water. So here you can see that we have sodium chloride dissolved in water. Sodium chloride produces sodium ions and chloride ions. So when each of these ions is interacting with water, for instance, the oxygen end of water would love this cation because the oxygen end has a partial negative on it. So that interaction would be an ion dipole interaction. And then when you have the hydrogen end of water interacting with the chloride ion, that would also be an ion dipole force. So when water molecules surround, or other solvents surround ions in solution, it's called a hydration shell. This is what it looks like here in the figure. But I just want to emphasize this only exists in solution. Nothing on that lab is in solution. Okay? Okay. So